Okay, hello and welcome back to this next part in this Twitch live series where we will code up the LDSO Twitch version. LDSO, that stands for Direct Sparse Odometry with Loop Closure. And in the last part, we have finished the full system.cc file. And in order to finish that, I have created 10 video parts. Let's quickly take a look at that. So these are the recordings on YouTube. And I realized one thing. Up until now, the whole video series contains about 30 hours of video content. And the thing is, we are not even halfway through the code. So I realized that things take too long to be efficient. So there's a change of plan. That is, I will not write out every line of code, but from now on I will start to copy and paste things from the original code base to this Twitch version in order to speed up things. I think this is a better way because then we can concentrate on the fun part, that is to try out things, to change stuff in the code, and I think this will be hopefully a better idea. So that's the plan. And the goal for this video, for this part today, is to actually finish the whole original code base so that you can try to finally run this custom implementation here on one of the standard datasets. We'll see how this turns out. So let's continue. Let's quickly take a short look or a quick look over this full system.cc file. And there is one thing, and this is the constructor here. So we construct the full system, and in order to construct the full system, we only need to pass the vocabulary. So the ORB vocabulary that is usually used to detect loop closure candidates, and gives us a way to have like a database of specific words, like a bag of words, and with this we can do the loop closure. But there are many other things. We have a course distance map, a course tracker for new keyframes, a course initializer, an energy functional, an calipation, and a global map, which all are separate classes, and they will be initialized with this C++ syntax. So when the full system is being called, then also these objects will be created and initialized. So those are classes that we need to implement, and I will start with the classes that are included on top here. So like the feature class, the frame class, the point class, and also the camera class that is used here, and the map class. So let's create them first. But before we do that, we should make sure that we are actually including this full system.cc file in the compilation phase. That is, we need to change the cmakelist.txt file. So in this source directory, we have this cmakelist.txt file, and here we have specific files included already, and we also need to include the full system here. So let's see, the full system is in our front end folder, similar to the undistort class. So we need to add the full system at this point. So I will copy that line, put it here, and change this undistort to full system.cc. I hope I have written it correctly. Let's check. Source directory and full system. Here it is in red. Clear to see. And with this, it is included in the build process. And we will have to do similar with the other classes. There is also the feature.cc file that I think I have left empty. Yes, the cc file is empty. And do I have a header file? No, there is no header file. But there should be a header file. So let's create it. So in this include directory, we have several header files. Some of them are created already from the last parts of this live stream. And now we will create a new file here. And we will call it feature.h. So this is our header file for the features. Let's copy the code from the header file and discuss it. So here is the code. It has about 100 lines of code. And luckily there is an explanation here. So let's quickly read through it. So the feature is a 2D point in the image. A triangulated feature will have an associated 3D map point, but an imager feature will not. Instead, it has an imager point. So we have the feature, and the feature is somehow related to an image. It is a 2D point in the image. So we will have some kind of data structure. I think it will be called frame to represent an image or a frame of a camera. And in this frame, we can have several features. And we can use those features to triangulate them, which will generate a 3D point out of this 2D point. So this is basically what this description is telling us here. Then there are some specifics like an imager feature or an imager point. And this will tell us that we do not have a 3D map point yet. So we have an imager point, which means we only have a 2D feature. And we can also have a 3D point associated to this feature, which will then be a 3D map point. With this feature, we can access the host frame and the map point. So when we have this feature, we can move from this feature to the frame and also to the 3D map point. This feature may have a descriptor, like an orb descriptor, which is currently the one that's being used. ORB stands for oriented, fast, and rotated brief, which is a descriptor, and the descriptor is basically a description of an image region. And this descriptor is there if the feature is a corner. So there's also a property called isCornerIsTrue. And otherwise, the descriptor, angle, and level are always kept as the default value. So there are many more things. There's not only the descriptor, but there's also an angle, like how is the feature rotated in the image, like what angle is it rotated at, and there is also a level. I don't know what this level specifically means here. I think it's the level of the image permit. So if you have an image that is loaded into the LDSO, this image is scaled down in multiple scaled versions. And I think this level here is meant by that. And if our features are described using this descriptor, they can be used for feature matching. Feature matching is important when we are trying to find images that contain similar features. For example, when we want to perform loop closure, then we need to find those matching candidates so that we can create loop closure candidates. And there's also this concept of bag of words, and this whole part here is what usually one can expect in a feature-based SLAM. Okay, then there's a note. Outlier features will also be kept in frame no. If you worry about the memory cost, you can just clean them. Okay, so the other thing we need to pay attention to is that even though we have an image, and in this image we detect several features, some of those features might be outliers. That is, for example, features can, due to the motion of the camera, they can move out of the image, for example. And then they cannot be matched anymore, and if they cannot be matched, then usually we cannot calculate a 3D point out of those 2D feature locations, and yeah, this is just something we need to keep in mind. Okay, here we have a struct, not a class, but a struct that is defined here. And in the struct, we still have a constructor and a destructor, similar as with usual classes. And we also have an enum for the feature status. So such a feature, it can be immature, which is 0. And if the feature is immature, the IP, which is the immature point, I believe, will have the immature data. So this feature can be immature, or it can be valid. That means we have a valid map point, but the point may also be outdated or margined. So what this means is, to my understanding, that we have those 2D features in the image, and they can be used to triangulate map points. But when we move the camera, after some time, those features are not visible anymore, but they still represent like a 3D point in world space. That is, of course, not removed, but it is like only relating to some prior point in time. Literally. And we have the outlier. That means the immature point diverges or the map point becomes an outlier. Okay, I don't know what this immature point diverges mean. Diverges. Oh, okay. So this is probably during the optimization. So we have our 2D features and we are observing more frames, so more points in time with our camera. And we somehow notice that the feature that we have chosen in the beginning, when we first got this camera image, that this feature point does not really belong to an object that can be represented in three-dimensional space. For example, what I'm thinking about here is if we have reflections. Then when you take a photo of a reflection, then this might be looking fine, like in the sense of that this reflection really contains like a corner, for example, or a specific object. But once you start moving the camera, this the projection of this reflection will change depending on your viewpoint, and this will make it hard to reconstruct a 3D point. I think it's still possible to reconstruct this reflection as a 3D object in 3D space, but I think this will rather lead to problems here. This is my experience, that reflections are usually bad for this kind of Visual SLAM system that we are using here. Okay, and this is the status of the feature, so we have those 3 states. Okay, what else do we have here? We have the possibility to create a map point from the imager structure. So from an imager point, we can release this imager point data. We can release the map point, so the 3D map point. We can release all the internal data. And we can also save and load one feature. This is useful if, for example, we want to simply save the internal data of the Visual SLAM system. For example, for further analysis, or to plot the data in maybe in another tool, or we want to use the features that have been detected in this LDSO system and we want to do some further processing on that. So it's useful to be able to save and to load this feature data structure here. Okay, in the class itself, we have a status variable, which is of type feature status. We have seen this above. And the initial state of every feature is imager. Then we will have the host frame. So if we have a camera image, we can use this camera image to detect features in this camera image. And those features are related to what is called a host frame. Then we have UV, which is the pixel position in the image. We have the inverse depth, which is initialized using -1. So this means if the value is less than 0, this inverse depth is invalid. And this value will be filled or computed by the DSO or LDSO sliding window. So if you have an image sequence, the LDSO will pick several frames out of this image sequence and slide it over so that we are starting with a window of a specific number of frames. Usually that is, I think, 7 keyframes. And the more frames the camera will provide, the further we will slide this window. So that we pay attention that we will keep a window of a specific number of frames all the time. And in this sliding window, the optimization will run. Okay, then there's a pointer to a point, which we will need to implement here. So we will have a feature here, we will have a frame and a point. And this is the corresponding 3D point. And in the beginning, it's a null pointer that is showing that this is an imager point. So it is not a valid point because in the beginning, we do not know the 3D coordinate of this point or the 3D map point. Okay, then we have some feature stuffs. That is an angle, a rotation, basically in degrees or in radian rather. And we'll have a score of this feature, a so-called Shitomasi score. We can determine, is this a corner? And we have this level. So which pyramid level is this feature computed on? And we'll have an orb descriptor. And the interesting part about this is that this orb descriptor is simply a vector with 32 values. And this will tell us what kind of image region do we have. So if we have several images, and for every image we compute this descriptor or basically for every feature, I mean, we compute such a descriptor, we can then find what image regions in the first image relate from their appearance to other features in other images. So this is a very useful concept that we will make use of. And then we have a shared pointer to an imager point, which is another data structure that contains specific information about this imager point. And this will be in the null pointer in the beginning as well. Okay, and this is the header file for the feature.h file. And we are still missing the .cc file of this feature, so let's first save that and close it. Or maybe before I close it, let's add, for consistency, this Twitch suffix to the LDSO here. Okay, and there is no comment at the end, so that's fine. And now let's go to the feature.cc file, and this is empty still. And let's also copy the code for the implementation. Okay, so here once again, we have this create from imager, which will just create this imager point. It will first assert if this is the null pointer or if this is not the null pointer. And if this is not the null pointer, then a new point is created and assigned to this local variable point. And also the status is then updated. Releasing the imager point and the map point and saving the feature and loading the feature is then very simple. And this is the feature.header file and feature.cc file. Let's double check if we have it here. Yes, we do have it in our CMake lists file, so we can continue with the next file. Besides the feature.cc file and feature.h file, we also need a camera.h file. So we need to have a representation for our camera. We call that camera.h. For the header file, come on, what takes you so long? Let me in the meantime close all the other files. We do not need them here. Can also get rid of the full system for now. Okay, now about the camera.h file. Let's copy that as well. And let's add our Twitch signature here. Hi Rahomo and hi Luigi. Nice to see you guys here. Welcome to the stream. Oops. The first mistake. So, to update you guys, I have decided to not code every single line of code as I did before, but now I will start to copy the code between the original code base and the custom implementation, just because I've realized we already have 30 hours of video content. Just don't have the time to really type out everything, and it's also not very efficient because of course we want to see what is going on in this algorithm, and that's why I've changed this strategy. I hope that's fine for you. Tell me if you have a different opinion, and in any case I'm always open to suggestions, so feel free. Okay, so now we have created this camera.h file, and let's quickly run through it. Yeah, makes sense. Okay, great. It's nice to know that you agree on that, so yeah. Okay, here we will have a forward declaration of the calipation, which we do not have yet, so we will create it later. But in general, this class for the camera, this will hold our pinhole camera model. And the pinhole camera model is usually a way to describe a camera mathematically. So the camera, the pinhole camera, will be described using 4 parameters. You can see that, or you can see these in the constructor here. So we'll have a focal length in x, focal length in y, and a principal point in x and y. This is everything. Those 4 parameters are everything we need to describe this pinhole camera model. The problem with this is that we cannot use this pinhole camera model to describe lens distortions, which we have in a real camera. So this is mostly useful for really like synthetic cameras, or when you're working with synthetic data. Okay, Luigi, I am deeply interested in the bundle adjustment. Yes, me too. But you will see the bundle adjustment, or the whole optimization, is something, yeah, well, let's wait for that. There's a nice comment that tells us what we should do with the optimization part of this algorithm, namely not touch it. And yeah, we'll see. Okay, then we will have methods to create and to release the ch, which is the calipation, which is in this forward declaration in C++. The forward declaration is useful, for example, for optimization, so that we can that the compiler can create more optimized code. So if it knows in the beginning what kind of classes it will use, then things can get optimized during compilation. It's useful for rectified images, right? Yes, so rectified images are images that are, as far as I know, undistorted. So you have your original camera images, they are distorted by lens distortion, they may have rolling shutter, they may have like chromatic aberration and stuff. And this rectified image is, for one that is using the pinhole camera model, and for 2 also, when we are talking about stereo cameras, rectification is also useful to align the epipolar lines to be horizontal. That helps us to do stereo matching. So you basically have a pixel in one image, in the left camera image, and you can simply find it by just searching along a horizontal line in the other image. So very interesting concepts and useful mathematical concepts that can be exploited here. And this rectification, by the way, if we remember back the undistorter, then I think somewhere here it was written rectify. Yeah, like building this rectifier, for example. So here's this word, and there's also rectifiers for the pinhole camera model, and in not this implementation, but somewhere the images are then undistorted and so on and so forth. Good explanation, thanks. I might make mistakes here. I have to say that I'm not like an expert as I would like to be an expert, but I try to at least explain things in a nutshell, as far as I can, of course. Okay, so we have this calipation here that is created in this camera model, then we can release it. And then we have internal attributes or fields. That is again fx, fy, cx, cy. And we have an internal structure to another calipation. This will be created in this create or released here, which is the mpch attribute or field. And this will be the null pointer in the beginning. Okay, and this is it about the header file for the camera. Let's now also create the implementation for that. So we go to the source directory, and in this main source directory, we'll create a new file called camera.cc. And now let's copy it as well. And this is also very simple. So we have the constructor here that basically just fills in the internal camera parameters, focal length and principal point. Then we have create calipation, which will create a new calipation, and release calipation will clean up. So it will check, do we have a calipation already? And if this is the case, we will set this to the null pointer. We'll set the camera of the calipation to the null pointer, and also the calipation itself to the null pointer. Okay, I wish everything would be that simple as in this camera.cc file, but unfortunately it is not. And the next file we will create, so we have this camera.h file. We will now also create the, so we have this feature, we will create the frame.h file. So in the include directory, we will create a frame.h file. Okay, let's copy this frame.h file here, and the first thing we will do is we will leave our, oh, there's no header guard here. Interesting. So let's copy the header guard from here. Or, no, let's not do this. Let's not get hung up by changes already. We will leave that for a later point. It somehow is just weird for me that there's no header guard here, but yeah, let's leave it. Okay, so what do we have in the frame.header file? Again, we have our namespace LDSO, and in this namespace we will have, now I know that why I do not have a header guard, because this is the CC file. It's not the header file, I'm sorry. Frame.h. There's still a lot that can go wrong with copy and paste. So now we have this header guard here, okay. And now let's add our signature. Like this. Okay, and now let's take a look into. So again, we have a for declaration here for the feature struct that we have just implemented before, and to the frame hash and to the point. This is again an optimization for the compiler. But here we have the frame struct. This is again a struct and not a class, but it still has a compiler. To be specific, it does have two different kinds of compilers. One that takes in a timestamp. So for every image we get from the camera, we can have an associated timestamp. And I will quickly fix this typo here, constructor with timestamp. Okay, similar to the camera class where we create a calip hashing. Here we create a frame hashing. So create a frame hashing that takes in a frame object. And we also can release this frame hashing. That is, usually we just assign the null pointer to the pointers of specific objects we are using here. We can also release the features. So release the internal structure in features and map points. Call this if you no longer want them. So again, there's a difference between features and map points. The features are basically 2D and the map points are 3D. And release all will just call release frame hashing and release features. And this is called when this frame is marginalized. So you have this sliding window, you have this image sequence, and within this image sequence you have several frames that are included in the sliding window. And when the sliding window is moving towards the end of the image sequence, the first frames are marginalized. And when they are marginalized, we call the release all on the frames that are falling outside of this sliding window. Then every frame will have a feature grid. So we can set that feature grid. And we can also get a specific feature in the grid given an X and Y and radius data. Then we can compute the bag of words vectors. This will take in the op vocabulary that we already know. And using this op vocabulary, we can create a bag of words for a specific frame. Then we can get the connected keyframes. So if you imagine you have this whole video with many frames in this video, then specific frames of this video sequence are keyframes. So something interesting is happening in this, like at this timestamp or time step. And if we have multiple of those keyframes, they are usually connected. That is, if you imagine that you are taking a camera and you are filming a specific object like a cherry tree, for example, then this cherry tree will be visible in many frames and therefore in also multiple keyframes, and those may be connected because they show a similar 3D point in this image. So we can get those connected keyframes that will return a shared pointer to a frame object, a set basically of shared pointers of a frame. Which BOW library do they use? They use DBO3. So if you take a look, is it in this? No, it's, I think. So you can see it for one in the vocab directory. There's the opvoc.dbo3 file, which is the one that is being loaded in the main file. So if I open the main file here, so here, for example, the full system is being created. We need to uncomment this when we are finished. I should not forget this. Need to think about many things here. I love cherry trees. Yes. Yeah. And Rahomo, the full system will create this. Will take this voc, and the voc is initialized somewhere here. Here with this op vocabulary and the voc path, which is passed onto into this as an argument to the main file. This will contain the this specific dbo3 file here. So if I go to the LDSO Twitch sequence. Then, where is it here? You can pass this vocab argument to this run LDSO Twitch to mono. And here you will see that here the obvoc debo3 file is being passed. That's everything I know. So I have never worked with bag of words and loop closure. I have never implemented it, so this is something new to me. Yeah, I don't even know what this vocabulary contains. So maybe we can find out together at some point. Or if you know it, I would be happy if you can just write it, or just write what you know, or maybe you can tell us what you have worked with regarding the bag of words, for example. So just feel free to let us know, or let me know. Okay. So we have been in frame.h, so we can also get the associated points. If we have this image, and in this image we have specific frames, every frame might contain, does not have to, but it might contain a reference to a 3D point. And yeah, this allows us to get all the 3D points, because this point data structure is, I'm not sure if this is a 2D point or a 3D point. We will see later when we implement that. Then we can save and load frames to disk, similar as we could with the features. Then we can get the pose of a specific frame. We can set the pose of a specific frame. We can get the optimized pose, which is optimized by loop closure. And we can set the optimized pose as well. And we have some global data here, unsigned long ID. So we have an ID of this frame. We have the next ID. So in the image sequence, we have specific frames. And those frames are, you can imagine this being like a linked list. So every frame points to the next frame. And this way we can quickly switch between the previous and the next frame. And there's also a specific keyframe ID for a frame. So even though the frame ID will be ascending, like 1, 2, 3, for example, the keyframe ID will, for example, be 3, whereas the normal ID is, for example, 1 or something. Depending on how the video is structured and how the keyframes are chosen, those may be different, the ID and the keyframe ID. Then we have a private scope. We will have a post mutex because we have multi-threading going on, and when we have multiple threads, they may access our data within the Visual SLAM. So we need to lock this data if we are, for example, changing the data, so that no other thread will change the data and create a race condition, for example. Then we have the poses with CW, which is pose from world to camera. And we have the pose from world to camera optimized. So this one is the global one, and this is, I think, the relative one. I've done a little bit of work with debo3. My understanding is that the actual words in the vocabulary are essentially sets of features that best let debo discriminate between different images in the training data. Okay. When running loop closure code for each image, you extract features, turn that set of features into a bag of words, and compare it against a bag of words that you've generated since the start of your trajectory. Okay, yeah. Sounds also like my understanding, but what I'm not understanding is this word. Let me quickly check. Understanding is that the actual words in the vocabulary are essentially sets of features. Okay, okay. So a word is, let's say, when we are talking about objects, and I have this cherry tree, for example, then a word would be a set of features that describe several parts of such a cherry tree, for example, like a top, like the trunk, branches, and so on and so forth. Is this how I can understand this, Homo? Then it would make, I think it would make sense, yeah. I think I got your point here. Thanks for the explanation. Okay, then we have a Boolean for the valid pose, if the pose is valid, so false when it is initializing. So it basically means we trust our pose. When we trust our pose or our current frame, then this pose is valid. A frame will have a timestamp, of course. It will have an affine light transform from global to local. This is what this G to L will stand for, or stands for. G to L, global to local. Then we will have a vector of features and a vector of vector representing a grid. We'll have a grid size, which is 20 here. 20 probably being the number of pixels for one cell. Then we have a mutex pose rel, so we have another mutex, we have a pose mutex and a mutex pose rel. But not sure if this is the relative pose and this is the global pose. Probably. Then we have a relative pose constraint between keyframes. So we have multiple frames. Oh, you have written right. Okay. Ah, great. Okay. Yeah, this makes it a little bit more concrete. Like your description turns this abstract concept of bag of words into something, yeah, something we can relate to, basically. Okay, I hope the sound is fine, the music is not too loud, and let's continue. Okay, so we have this relative pose struct that takes in a T, like a sim3, a similarity transform, that is rotation, translation, and scale. It will also take in an H 7x7 matrix, which is initialized using the identity, at least in this argument list here. And a Boolean is loop. And with this we initialize the TCR field, the isLoop field, and the info field. Oh, and now it's getting interesting because here we have, not sure what T is, probably transform, CR is camera and relative probably. Not sure what this should mean exactly, but this info matrix is the information matrix. This is the inverse of the covariance, and by default it's the identity matrix. And here it is also initialized using the identity. So the information matrix is the inverse of the covariance matrix. This is something we should keep in mind, because this will tell us something about the uncertainty of this relative pose. I think one of the first things I would do is to plot these values while the LDSO is running. Okay, here we have a map a map object of a frame and a relative pose and another frame. Okay, this is complicated. We have an aligned allocator of eigen with a pair of a frame and a relative pose. And this is called a pose rel. Okay. Relative poses within the active window. Okay, so this way we can probably quickly access all the relative poses we have in our sliding window, which is of course important for the optimization. So things need to be fast and we do not really search in one list what kind of frame belongs to another frame. So having this map structure will, I suppose, help a lot to find the right connected frames within this window. Then we have the bag of words structures. So we will have a bag of words vector, we'll have a feature vector, and we'll have an index of the bow-iced corners. Okay, I still don't understand what the difference between the the bag of words vector and the feature vector is. But I remember that there's a method that will convert between those vectors here. So this is probably a vector that is being used for the very efficient bag of words functionality, and this feature vector is, for example, used for plotting the data, to plot the features in the image and stuff. Then we will have a frame hashing, similar to with the camera object. We had a calip hashing, and here we will have a frame hashing, which is important because it will contain additional data, which we will know once we have implemented this frame hashing object. Then we have an OpenCV matrix, which is the image display, and this is useful to display this image for a specific frame, and this is only used for debugging and will be an empty image if the setting show loop closing is false. So only if we have the setting show loop closing set to true, this will not be an empty image. This is interesting. I think this is not a good idea to keep this as an empty image. I think there's always some interesting data we want to display for debugging. Okay, then we will have a class for comp frame ID. This will override the parenthesis operator or the function operator, and will take in two frames, F1 and F2, and return if they are so if frame 1 is less than frame 2 ID, so it will compare the two IDs of the frames. And we also have a similar function for compare frame keyframe ID, but this time it will take the keyframe ID and do the same. And that's it. That's it with the frame.header file. Let's save this again, and let's also create the implementation for the frame. So in the source directory, we'll create a new file called frame.cc. Frame.cc, let's copy that. Okay, so here we are basically just filling in the constructors here, release frame hash and release features, create frame hashing, we set the feature grid. Where we will fill in this grid data structure that was introduced as a member variable, I think. There's no grid here. Ah, here. Here's the grid. So this is the grid. So every camera frame, you can imagine every camera frame will have a grid. And in each grid cell, there will be features. There will be features detected in each grid cell. And we need to somehow fill the data. And this is being done here. So with this pushback, this I is then added, which is just the iterator over all our features. Okay, so we loop through all our features. They will have an ID, like an iterator, index and index. And this index will then be pushed into this grid structure by calculating the position where it should be. Okay, so every grid cell might have no or multiple features in this grid cell. Okay, we can get the features in the grid, so we basically make a search for them. This is, I think, bounds checking here. And if it's inside the bounds, we can loop through the whole grid with a nested for loop here. And also within a cell. And check if this feature point, the U and V coordinate, so basically the 2D coordinate of this feature, is within a radius, it seems. R2 is a radius squared. And if this is the case, then the indices are then filled and returned. Then we compute the bag of words. So we take a vocabulary. We prepare a vector of OpenCV matrices containing all descriptors. And then we loop over all the features and we fill in all desp. What is all desp? Okay, let's not get hung up here. We simply fill all the data structure that we have. And then there's some interesting function for the op vocabulary called transform. So we can use the op vocabulary to transform our all desp vector probably into a bow vector. Where is the bow vector? This is probably something, a field. A bow vec here and a feed vec. Maybe this will take the all desp and put the data somehow in the bow vec and the feed vec with this size of 4. Yeah. I don't know. Maybe at a homo you will know that, but I do not know what is happening here. And there's also no IntelliSense telling me what this is, so we need to debug this later if we want to know that. Okay, get connected keyframes, get points will return, so connected frames will return a set of shared pointers to a frame, and get points will return a vector to a shared pointer of points. Save will save out the information about a frame, that is the matrix from, was it from camera to world or from world to camera? I'm not sure. Where was it? Here, post from world to camera. So TCW is from world to camera. So, oops. You have to read it from right to left, world to camera. This is being written into the file. And we also have the features written there. I just use the function that takes in a CVMAT of descriptors and gives you a bow vector. Okay. And what is this function called? That takes in a CVMAT of descriptors? It's probably also the same, right? It's probably also the transform. Because this is the CVMAT of descriptors. This is a vector of CVMATs. Okay. But there seems to be another function that takes in simply a CVMAT of all descriptors and converts it to a bowvec. Okay. And then the bowvec can be... okay. Vocabulary transform, I think. Okay. So it seems to be the same. Just an overloaded function. Okay, interesting. Okay, so we save the matrix. World. And we write features. Maybe let's put it here. And also the relationship with other keyframes. Okay, then we will have the same for loading. Or rather reading. Okay, the reading is rather here. And then we have this relationship, which is probably here. Okay, but that's it with the frame.cc file. Okay, not to forget, we need to add those files to the CMake lists file. So we have the feature, we need the camera.cc, and we need the frame.cc. And that's everything, I think. Okay. After the frame, we have the map object. So let's go to the include directory and add a new file called map.h. And let's add in Twitch here. And let's go over this. So we have a forward declaration of the full system. And we have this main part, the map. This will take in a reference to the full system and initialize this full system member variable, which is somewhere here. Yeah, at the end of this file. And in this map object, we can add a keyframe, which takes in a shared pointer to a frame. We can optimize the pose graph of all keyframes, optimize all keyframes. Or we can optimize the pose graph on all keyframes after the odometry loop is done. What is the odometry loop? I think this is just the simple image alignment process. We can update all the world points. So usually when we have a sliding window and we are optimizing within the sliding window, we are moving around the camera transformations. So we are changing the camera extrinsics. And when we change the camera intrinsics, the 3D points are outdated. So then we need to update the 3D world positions of the points. And this is being done here, it seems. Then we have a getter that gives us the total number of frames that we are storing in our global map. Okay, so the map contains at least the pose graph, so basically the trajectory our camera was moving along. And the map will also have a way to optimize this trajectory somehow. We can check if the map or the pose graph is idle, so if it is running. For this we need to lock all the poses or this pose graph. And once we are locking it, this will be locked in this scope. So within this method, we will lock the pose graph, and then we can check if the pose graph is running. And then we are releasing it once we are leaving this scope. Then we can get all the keyframes, which will return this frames member variable. And we can get the latest optimized keyframe ID, which will return this keyframe ID. Okay, then we have a private scope. For example, we can run the pose graph optimization. So once again, we have our image sequence. We have connected frames within this pose graph, and we want to optimize them usually using some kind of residual. This is what Luigi, I think, wanted to know. So this is probably one of the bundle adjustments available here. But there are many bundle adjustment steps. So Luigi, in case you are still listening, I think you need to define what bundle adjustment you want to learn more about. You want to learn about the bundle adjustment that optimizes an image pair, or do you want to learn about the bundle adjustment in the sliding window, or do you want to learn about the bundle adjustment in the loop closer? Or yeah, I think there was at least 2 more bundle adjustments. Okay, then we have a map mutex. We have a set of frames optimized. And we have a pointer to a specific frame, which is the current keyframe. Then we have an unsigned long for the latest optimized keyframe ID. Then we have a boolean which tells us if the postgraph is running, and we have a mutex for the postgraph, and we have the full system reference. Okay, this is the header file. Let's now copy or create the map.cc file in the source directory, map.cc. Okay, so here we have add keyframe, last optimize all keyframes, that is final postgraph optimization after odometry is finished. Run postgraph optimization. Okay, so the difference between the last optimize all keyframes is that this is, it seems, not multi-threaded, but this optimize all keyframes is multi-threaded by creating a new thread and detaching this thread. Which will internally set postgraph running to false, whereas here it is set to true. Okay, where is this function? It is here. Okay, so here is this mighty bundle adjustment. But before that we have the update all world points. And here we loop through all the frames, and in each frame we loop through all the features. And if the feature does have a point, we will compute the world position of this point. Simple as that. So we are just updating the world points, as the name suggests. Okay, so here we have this postgraph thread, and this is using G2O. So G2O is a quite popular library for postgraph optimization. And it's interesting to see, for example, how G2O is used here. So first, a sparse optimizer is being created. So sparse optimizer, to my understanding, because we have huge matrices, but within these matrices, only a few values are non-zero. So we need intelligent methods to work with those large matrices, given this information that there is only like a sparse number of entries, non-zero. And this is what the sparse optimizer, I think, is being created for. Then we will have a block solver type, which is a linear solver type. And now it gets complicated because this will take in the post matrix type. And then link this linear solver type with this block solver type. And then the authors of LDSO have prepared different types of optimization algorithms. This one is the Levenberg-Marquardt algorithm, it seems. And we have Gauss-Newton, and we have this dogleg, which I do not know about. But here Gauss-Newton is being used. We give it the solver pointer. Then we set the algorithm for the optimizer and set the both to false. So I think this is maybe something interesting. This might give us some information. Okay, and then once this is initialized, the optimizer is initialized, we need to set up this G2O data structure, which is created using vertices and edges. So you can imagine or think of the vertices as being the poses in this graph, like the pose graph, and the edges, like I think the vertices are the absolute poses and the edges are the relative poses that just link those poses together. And for every such vertex, we need to set an estimate, maybe like an initial value as well, an ID, and then add this vertex to the optimizer. And we can also fix several vertices. Now here the edges are created by setting a vertex and another vertex and a measurement, which is a relative transformation. We set an information to the edge, and then we add the edge to the optimizer, and then basically the optimizer only contains vertices and edges. And we can initialize the optimization and optimize, simple as that. And then we can, I think, extract the optimized values from the optimizer by looping over the frames and using the ID by calling optimizer.vertex to return the sim3 transformation. And we can get the estimate from that. And this way we get a sim3 transformation. And this can be then used to draw the trajectory or to print out the values or do whatever with that. Of course, we need to set the optimized pose for a specific frame using the value that we just extracted from the optimization. And as we just changed the frame orientation, we also need to compute the world position of the points again. Then the pose graph is not running anymore, so we set it to false. And we clean up. So we set the latest optimized keyframe ID to the current one. And we need to refresh the graphical user interface of the full system. And this is it with the map.cc file. Okay, let's close this and let's add this file to the CMake lists. All right. Now we are missing the point data structure. So let's create the point.header file in the include directory. Let's paste it here. And this time there's no include guard. And I do not want to change anything at this point, but I will add it to add the include guards here. Okay, so here we will have the forward declarations again, as usual. I have read that adding forward declarations in the code is usually always a good idea. I'm not sure how true this is, but it seems to be consistent in the LDSO at least. And now we have the point data structure here with two constructors. One is a default constructor and the other one takes in a host feature. That means points can only be created with a host feature. It will try to create a point Hessian from the imager point stored in the feature, but if it doesn't have, will create an empty point Hessian. So there is this point Hessian also related to the point, similar as with the frame and camera. So frame Hessian and calip Hessian, we also have a point Hessian. We will have a point status, which can be active. The point is still active in optimization. It can be outlier, which means considered as outlier in optimization. It will have the status out if it's outside the boundary. And it can be marginalized. Marginalized usually also out of boundary, but also can be set because the host frame is marged. Okay, so if the host frame is moving out of the sliding window, we can set the point status to marginalized as well. So if the frame is marginalized, the point will also be marginalized. We can release the point Hessian. And we can compute the world pos. We saw that in the map data structure. We can save and load a point, and each point will have an ID. It will have a next ID. It will have a status. It will have a world pos. So every point will have an associated 3D vector, which is 0 in the beginning, which will tell us the 3D position of it. And this is obviously not in camera space, but this will be in world space, it seems. And it will have a host feature of type feature. And this is a weak pointer. Not a shared pointer, but a weak pointer. Okay. Here we have a map point Hessian. Is this MP really map? How can I find out? I can't, it seems. Okay, but we will have an associated point Hessian for this point. Let's save that. And let's add the point .cc file in the source directory. Point.cc. Okay, so here we have those two constructors that will both initialize the ID of the point. Then we will have the release point Hessian, which is again just assigning the null pointer to the important data structures. compute world pos is taking the optimized pose, the inverse of that, and also calculating the point. Okay, it's the k inverse, so it's the inverted fx, fy, and cx and cy. So this is the inverted camera pinhole, not kinhole camera. It's the inverted pinhole camera model, that one. And this is used to transform the point using its u and v coordinates in image space, and then transformed using the inverse into camera space, using the inverse depth to scale basically the ray in camera space, and then transformed here to transform from camera space to world space. So from camera to world transform will give us the world position of this point. Seems complicated when we look at the math, but I think yeah, thinking about it in with more time and by concentrating, I think it's quite easy. And then we have save and load, which simply writes and reads the point data structure. And this is it with the point.cc file. Let's not forget to edit here. Okay, so these ones have been the easy files. Let me quickly double check if we have everything regarding the top level source directory. So let's close frontend and internal. Here we have camera, CMake lists, feature.cc, frame.cc, map.cc, point.cc, and setting.cc. And in the include directory, so for the header files, we have camera.h. Okay, we are missing one file here. So in this include directory we'll add flight.h. So this is our affine light data structure. Let's copy that. Let's add the Twitch signature here. Okay, it seems simple. So we have this affine light function or data structure here. Use A, B here to describe the exposure change. CDSOs, paper for details. Okay, let me quickly look that up. If I can type. Okay, so here I have this archive-x paper, direct spatialometry. Let's get to the PDF file. Let me check if I can quickly find it. I think this image is one we can use here, but it's not really clear. Okay, but I think what the commit is telling us is this main error or residual formulation. So here we have our first image, like let's say, not let's say, but I think this is the target frame and this is the host frame. And we have this parameter bi and bj, and we have ai and aj. So these are used, like this a is used as an exponent in this exposure ratio here, and the b value is used as a brightness change. So I think b is the brightness parameter and a is the contrast parameter. So this is a factor. A is a factor on this host frame, and B is an addition or subtraction term on the image brightness. Okay. So we have those parameters A and B, which are ideally provided to us, but usually we need to estimate them during the optimization. And the authors of LDSO and DSO, they are just introducing a separate class for that using this struct. And we are constructing the objects either without parameters or by using the specific A and B values, which will then be used to initialize the member variables here. And here once again we see the same formula as in the paper before. So we have this I frame, which is the exponent of A times the intensity plus this B value, or in the paper this was a minus. It was also written a little bit different. Okay, here it is a minus, I see now. So exponent of negative A, let's quickly compare that to the paper. Okay, but here the exponent is not negative, but positive. Yeah. So there are some differences, maybe I'm not spotting them at the moment. But those are the A and B parameters that are meant here. And there is a method called from to vec exposure. So it will return a vec2 of basically just those parameters here calculated or combined. Audio's cutting in and out, or is it just me? I hope it's just you. I'm not sure. From my side, it seems that I have a stable connection. Maybe it was just me thinking and like cutting my voice. So I hope it's fine now. Let me know if this problem persists. Okay, but this is everything for this affine light data structure. So let's just save this. And let's continue. Okay, let me quickly check. So finalize.h. Then we have camera. Then we have the dataset reader, which I interestingly put in this include directory and not into the examples folder. So in the original LDSO, the dataset reader header file was in this example folder, but I think I didn't like that, so I have moved this here. Shouldn't make a big difference, I think. Then after the dataset reader, we have feature. After camera, we have feature. Then we have frame.h. Then we have map.h, numtypes.h, point.h, and settings.h. Okay. So we are finished with the top level include directory. But we still have this internal directory and the front end directory. Let's continue with the front end directory. Okay, and in the front end, we will have all the files that are related to like the first processing of images that arrive. That is, for example, we need to undistort the images. First, we need to read the images, read and write them. We have that. We need to undistort the images. And then what is usually being done is we need to detect features, we need to match features, and we also need to initialize the full system, and we need to track those features across the image sequence. We need to have a user interface where the user is interacting with the software, and all of this is usually part of the front end, which is a lot, but very important stuff. Okay, so let's create a new file in the front end, new file, and the one we are missing first is the course initializer dot. Okay, I'm in the CC files again. Let's put this here, and let's also create the header file. Course initializer.h. Initializer. There's a big chance that I have a typo here, but I hope I can find that. Okay, course initializer. Let's copy that. And let's put the Twitch copyright here. All right. So the course initializer will first define a struct called PNT, probably because point was already taken. So this is a point structure used in the course initializer. So the course initializer will have a separate data structure called point. Why? Who knows? And then this PNT data structure will have a U and V coordinate. This is the index in Jacobian, never changes. Actually, there is no reason why. Okay. It will have an I depth, which is probably the inverse depth. It does have an is good and an energy during the optimization. This makes sense. Okay, there's an U energy photometric. Which is probably a typo here. Okay, then there's is good new and I depth new and energy new. So there's an old inverse depth and a new inverse depth. Then we have this cryptic IR sum num, last Hessian and last Hessian new, a max step size for I depth corresponding to maximum movement in pixel space. Okay. And we have an index of closest point 1 pyramid level above. Okay, so how the coarse initializer is working, it will take in an image that will be the host frame, and then we'll take in an image that is the target frame, and it will scale down those images to a very low resolution image for both host and target frame. And then in this coarse resolution images, it will try to find the matching image intensity. And this will be done by optimizing the camera motion, so the relative camera transformation between host and target frame, and the inverse depth, which will lead to the possibility to create a 3D point. And this 3D point is created from the host frame by taking this feature point in the host frame, using the inverse depth to create a 3D point out of this 2D feature, and then projecting back the 3D point into the target frame, and then looking at the intensity difference. So when we take a look at the DSO paper, then this equation number 4 is basically the one we are looking for. So we have this first intensity in this case the target frame, I think, and here's the host frame, and we are simply just subtracting both intensities from each other. We adjust the intensities using the exposure time and the B and A values. And we do that for every point in this neighboring residual pattern, which is this one. This is the residual pattern, NP. And we simply sum all these residuals and calculate this error term. And the goal is to minimize this error term. Now here only the intensities are visible. So where is the depth, the inverse depth, and where is the camera transformation? And this is defined when we look at the definition of this P prime point. This will be in another equation. I'm not sure which one. I think it's here. Yes. So here P prime is defined using, we start with this part of the equation. So we have our point in the host frame. we combine it with the inverse depth dp, inverse depth dp. Then we use the camera model, the intrinsic camera model. So this is this projection function, but we use the inverse of that to move from our image space to camera space. Then we multiply that using the rotation matrix and adding the translation vector to transform from camera space to world space, because these coordinates are given using world space. So this is the transformation from camera space to world space, I would say. And then using this projection function, we are then again moving from world space to camera space using not the inverse but the normal projection function. And then we get this P prime, which is basically the feature point in the target image. It is a bit complicated to understand this. So implementing this equation will probably make things a lot clearer. And this equation is somewhere hidden in one or multiple of these files, and I'm not sure where. But probably in some kind of bundle adjustment region. Yeah, maybe we will see it at some point. Okay, so this is why we need this inverse depth, and we need to know the pyramid levels, and we need to index them, and we need to know neighbors. Yeah, and this is all that is stored here. And this is the interesting my type that was featured in one of the comments in another file. Okay, but this is the PNT data structure. We are basically looking into the course initializer here. So we have a constructor and a destructor, and we also have a method to set the first frame, which will take in a calip Hessian and a frame Hessian. This course initializer will also be able to track frames and to calculate some gradients using a new frame Hessian. And this course initializer will have fields for the frame ID, for whether it should fix the affine parameters, the affine light parameters, I think, and if it should print some debug information, and it will also hold a pointer to this PNT data structure, which is an array for all the number of pyramid levels that we will have. So all the scaled down image versions. If it will also have an array, how many points we will have at each image pyramid level with num points. It will have an affine light object that tells us the affine light from this to the next. And it will also have the SE3 transformation, that is translation and rotation from this to next. It will also store a shared pointer to a frame Hessian for the first frame and for a new frame. And it will have a copy of the pinhole camera model inverted and normal. So there is K and Ki. So K is the, yeah, we could say maybe that K is this here, this capital Pi function, the projection function. Within this Pi function, we have those fx, fy, cx, and cy parameters. And we also have the inverted version of that. So this will be this pi c inverted here. And then we have the individual values of those matrices or this function like fx, fy, cx and cy, and the inverted variants of that. And also the width and height of our images for every image pyramid level. Then given a calipation, so a camera object, like a pinhole camera model, we can make k, which will probably fill these values, I believe. Then the coarse initializer will have a boolean called snapped, and an integer snapped at, which will probably tell us at which frame ID this coarse initializer snapped. What the snapped means is, I think, an indicator for whether we are initialized or not. And then we have a pointer to vector 3f, so to a 3D vector. For every image pyramid level that stores the pyramid images and levels on all levels. Okay, this is a bit confusing. DI new, DI fist. Okay, not sure what this is at the moment. Then we have a diagonal matrix of dimension 8 called WM. Width matrix. Not sure about this either. Then we have temporary buffers for H and B. So this H and B is, I think, related to the to solving linear systems. Like, I think it is how was it? I think it's AX equals B or something like that, and A is probably H. This linear system, I'm not sure at the moment. Okay, then we have some buffers. And now it's getting really cryptic. It contains 0 to 7. So we have a 10D vector. 0 to 7, the first 8 elements contain the sum of dd times dp, 8 the sum of res times dd, and 9 1 over whatever the inverse Hessian entry. Okay, so these are specifics to the bundle adjustment and optimization. Which I will not be able to grasp in this part, I think. But we have some accumulators. Then we have, I think, gradients for every pyramid level. Alpha k, alpha w, rec weight or coupling weight as well. So those variables are really cryptic to me. It would be nice to know what they are and what they do. But in any case, we need to calculate a residual and, like, I think Gauss-Newton step or something. And we need to calculate an EC, which is probably energy cost or something. Returns old energy, new energy, and num terms. This is probably energy. And we have an opt rec. Oh my gosh, this is really, really complex. Propagate up, propagate down, which is probably related to the image permit. So once we are starting to optimize on the course's permit level, we at some point need to take our estimate and propagate this one level up. And similar, we need also to do this in the inverse direction, so down. And so we pass in a source level, and it will then go up or down depending on this level that we pass here. We need to rescale something. We need to reset the points for a specific image permit level. We need to do a step on a specific image permit level using a lambda and an incrementing vector. We need to apply the step once we did it. We also need to make gradients. And make an n is probably make nearest neighbor. Okay, then we have a minimal flan point cloud. Flan stands for, I think, fast linear approximate nearest neighbor or something. Let me quickly look that up. Okay, fast library for approximate nearest neighbors, it seems. So this helps us to get really fast searches for the nearest neighbor in high dimensional spaces. It's licensed under the BSD license. And here we can define a point cloud that takes in a number and a pointer to many points. Then we can get the KD tree get point count, which will return a number of points. Can calculate the distance. Can get a specific point by using an index and a dimension. Then we have a templated method where we can get a bounding box, a B box. But this will always return false, which is weird. Oh no, it will, okay, it will return a boolean, but still always return false, which is still weird. Okay, so the course initializer is, yeah, a part of the algorithm which is very important because it will create the first initial values for our optimization. And this is where things can fail. And when they fail, this will be bad for our algorithm. And I hope we can demonstrate such cases by creating our own dataset and running it through the LDSO. Yeah. Alright, so this is the header file. Let's take a look at the implementation. So course initializer.cc. And now you can see how much time we have not spent, but how much time we have saved by just copy and pasting. This would take definitely like a few hours to type out. I'm not even saying how much time it would take to start thinking about what is happening here. And to be honest, I will not do it in the stream right now, not starting to think, because I think without running the algorithm, many things will still be like speculation. And this is not helpful to speculate on things. So I would say we just save that and leave it as is. But of course we need to add this to our CMake lists file. So this was a part of the front end. Course initializer.cc. Okay, let's continue with the course tracker.header file. So in the front end we will have a course tracker.h. Let's copy that. And let's add Twitch. And let's make a quick run through over the course tracker. So it will have a constructor and a destructor. The constructor will simply take in a width and a height, and will allocate memory and compute the camera intrinsics parameter. I think the same is being done in the course initializer. So we'll see if this... Oh, this will also have a make k at least here. But it will also track newest course, track the new coming frame, and estimates its pose and light parameters. Okay, so this will return a bool, but it will internally estimate the pose and light parameters, which will be passed here. So we pass a new frame hashing, and we pass a reference to the last to new out, and affine global to local out, and also the coarsest level ID and the minimum resolution for abortion. Residual for abortion, I mean. Okay, everything is explained here as well. And we also set the course tracking reference. So we have a reference frame hashing and a new frame hashing, and those two are used, it seems, to track the camera. This make K takes in the camera intrinsics and creates a buffer given this calibration parameters. So somewhere, okay. Now you can see one of the big issues I noticed with the LDSO is that data is scattered all around the place. You can see it with this pinhole camera model. It's basically the same as we had it in the coarse initializer. So yeah. And this data will probably not change for one specific data set. So why is it not shared across like coarse initializer, coarse tracker, and maybe also other classes? This is something I noticed that this happens from time to time. And unfortunately, this makes debugging and extending the LDSO more complicated than it should be, I think. Okay, act as a pure output. Okay, so we store the last residuals and the last flow indicators, which will probably also be interesting to plot at some point. And we also measure the root mean squared error of the coarse level. And this is something we probably want to improve upon. Okay, but this is it about the public scope. And in the private scope, we have a make coarse depth L0. Then we calculate the residuals. It will return the residual vector, a bit complicated. That are last lines in this func. I don't know what this means. Probably the last lines in this file, or... Okay. So in this function there will be some lines at the end which are a bit complicated, it seems. But we do know that from the LDSO, right? Okay, then we have some calc GSSSE. I think it's called GSSSE, which is the SSE accelerated Gauss-Newton. So this LDSO is using an instruction set called SSE. There are multiple versions like SSE1, SSE2, and SSE3, I think. And here I think SSE3 is being used. And we will see that at some point. I do not know anything about it, so I will not bother to look it up now. Let's just continue. We have some point cloud buffers of type float. For every pyramid level, we store the U coordinates, the V coordinates, so basically our image coordinates, our pixel coordinates. We have the inverse depth in the reference frame, like the host frame, I would say. And we have the color. And we also keep track of the number of points in each pyramid level, or layer as it is called here. Pyramid layer, pyramid level. I'm tempted to rename that to level here. Okay, but then we have the warped buffer. used as width times height images. Not sure what this exactly means. I think warped is related to when we take our host image and we take the individual pixels of that host image. We can warp them in such a way that they align with the target image. And of course we need a buffer for that. But I'm not sure if this is exactly what is meant here. Okay, then we have a buffer for the eye depth, the inverse depth for every pyramid level, the weight sums, and the weight sums back. Then we have some pointer to delete, vector of float pointers. All allocated memory will be deleted in deconstructor. Okay, do we have a destructor here? Yes, so okay, pointer to delete. We loop over every pointer in that and delete the pointer, and then we clear this vector, the standard vector. Okay, then in this course tracker we also have this course distance map, which we already saw in the full system. And this will have a constructor and a destructor, which also takes in the width and the height. And we can make the distance map, make a K. Once again, we are storing the pinhole camera model and the inverse pinhole camera model. We have an add into dist final with U and V coordinates. And we have some private fields, course projection grid, a double pointer, and we have a course projection grid num pointer. And we have a BFS list 1, BFS list 2, whatever this is. And we have a grow dist BFS, with a BFS num passed as an argument. BFS. What is BFS? It's not clear from this header file, but let's take a look at the implementation. So in the front end, we will create a new file called course tracker.cc. And let's paste the code here, and you can see that this is already quite cryptic here. But let's try to go over the clear parts. So this starts with a very interesting alloc aligned. Create an aligned array and send their pointer into raw pointer vec. Okay, I don't know. There's some pointer arithmetic magic happening here. Okay, let's go to the course tracker. For every level in this image pyramid, we define a width for the level and the height, and we initialize the member variables for the point clouds and the inverse depth and the weights. We also directly initialize the buffers for the warped result, and we set the width and the height of image pyramid level 0, which is I think the finest, to 0, which is weird. Why would I do that? Let's add this as a question. Okay, we can track the newest course, which takes in a new frame hashing and spits out the last two new out and the affine light out. So here I think we have some kind of bundle adjustment happening. We have some iterations for each level and solving a system here. Those are definitely all interesting things we can look at when we are running the algorithm. This is quite a lot. Make k should be simple again. We just initialize all the internal fields. Set course tracking reference. We take the last frame hashing in our list and set the frame ID of that and the affine global to local. We have make course depth. We are initializing the inverse depth and the weight sums. Then we are looping over various things and also initializing the values of I depth L and weight sums L. Okay, this is an interesting pattern. It seems like it uses the neighboring pixels, starting for example at the bottom left and then top left and then going to the top right and bottom right and summing all those values up in this num and sum variables and using that to update the internal fields. Then it is using a similar thing, just differently. And then it's normalizing the I depth and the weights. Then we have a calc residual method, which is probably where we have this energy term from the paper. Huber. We have this Huber threshold, which is in the paper, I think. So we have this barely noticeable gamma symbol here, which is denoting this energy term as a Huber norm, which seems to be more robust than other norms like the L1 or L2 norm. So I think somewhere here there should be this formula written out. But I do not see it at the moment. I think this is probably this line. So we have this hit color 0, minus the reference color. So this is probably the host frame, the reference frame, and this is the target frame. And at this target frame somewhere we hit a specific color, and when we subtract them, and you have this affine light 0 and 1, which is probably A and B here. If you hit this color and subtract it from the reference frame, I think you get to this kind of formula. What I'm missing here is that this affine light parameter B is not subtracted from the target frame here. But this was probably done at some other line of code. Even though I do not see it here. Yeah. Something that needs to be checked at some point. Okay, and returned is our S, which is a 6D vector, which contains some energy, num terms in E, and something about the translation, rotation and translation, and some num saturated. Okay, here we can see calc GS, the Gauss-Newton step, using SSE will lead to these interesting instructions, which start with this kind of data type here, and yeah, are quite cryptic. Then the course distance map is created here and deleted. Make K is similar to the others, I would say. And this make distance map will create this distance map. Let me quickly check if we can see what BFS stands for. BFS list. Okay, so it will, after all, it will contain the U and V coordinates of our points, probably. So it could be something. The BFS list could be something related to the errors of our points. Yeah, but I'm not sure. Grow distance map, BFS. Okay, let's leave it for now. This is too cryptic to go over this. But we will add it to our front end. Course tracker.cc. And let's continue with the DSO viewer. So in the front end, we create a new file called DSO viewer.h. And this is, again, a very central part of the LDSO, because this is where we as humans can interact with this Visual SLAM system. This is basically the 3D viewer. Something we will dissect a little bit further at a later point. Let me just add the signature here. Okay, this is very interesting to go through, but I will not do this here. I think I will finish copy and pasting the stuff, and then we can spend some more time in this DSO viewer, because one thing that I will probably do is to add the drawing of a grid of our like X and Y world plane, because I noticed that this helps, and I also added this code to the DSO a few years ago, so I think this will be a useful addition. So I will do that on the live stream, I think. Let's now create the implementation in the front end. DSO viewer.cc. DSO viewer.cc, and this has almost 700 lines of code, which is not a lot, and the code is mostly easy to understand, I would say. Especially the drawing code. It uses OpenGL, and this is yeah, easy to understand, I would say. Okay, so this is it with DSO viewer.cc. Next, oh, we need to add this here. Next, in the front end, we will add a new file, which is the feature detector.header file. And this is a rather small file, but this is only the header file. So what this is doing is it is detecting corners and computing the descriptors, and also drawing features if we want to draw those onto the images. And it is also computing the Shitomasi score, which is written out completely here. It is calculating the angle or the rotation. And this is basically it. So in the front end we have a feature detector.cc file in the source. And what I just told you about the small file size with about 100 lines of code, you will see that here we have almost 500 lines of code, and this is mainly due to these hard-coded values which is a mean and a correlation, it seems. And typing this out on Livestream is a nice waste of time. And I'm happy I will not do that. But in the end, you can draw some features here. You can compute the descriptors here and detect the corners here. And this is basically it. This is the feature detector. It's in the front end / feature detector.cc. Now in the front end, we also need a feature descriptor. No, it's a feature, sorry, a feature matcher.h. Feature matcher.h. This is using the features and matching them using nearest neighbor search. And we can see that we can initialize or create a feature matcher using a nearest neighbor ratio. If we want to check the rotation, that's it. It will calculate an integer for the descriptor distance. It will be able to make a search with a brute force approach or a search by bag of words. And we can also draw the matches on on 2 frames. And this is basically it. So let's create the implementation for that. Feature matcher.cc. Like this, and here we have some optimization using SSE2, which I am using here. And there's this comment, SSE is so easy, because it's just a single line of code, whereas without SSE2, the code is much more complicated. So things can be easier too. This is the brute force search. This is the bag of words search. And there are some comments here in, I think, Chinese. Let me see if I can translate that. So this is translated to recent. And this one is translated to second closest. So I will just replace that because I cannot read this, the Chinese characters. Can draw the matches using OpenCV by circling the 2 images, the first image and the second image, and drawing lines in between them. And showing the image. Okay, and this is the feature matcher. So let's add it to our CMake lists file. feature matcher. Next we have the full system, which we already implemented. This was very hard work. Then we have the image and exposure, which we already have as well. Then we have image RW, which we already have. And next, in the front end, we have the loop closing.header file. And this will implement the loop closing thread, which is also used for correcting loops. Loop closing is running in a single thread, receiving new keyframes from the front end. It will separate all keyframes into several consistent groups. And if the newest keyframe seems to be consistent with a previous group, we say a loop closure is detected. And once we find a loop, we will check the sim3 and correct it using a global bundle adjustment. So we are searching for loop candidates, and once we have them, and we are sure of them, this is the important, the difficult part, of course. When we are sure of that we have detected a loop, we'll check the sim3 and correct it. So we want to correct not only the rotation and the translation, but also the scale. And this will be corrected using a global bundle adjustment. We have a constructor and destructor. We can insert keyframes, we can detect loops, we can correct loops. Then we have this run function that will probably contain an infinite loop. And we can set that we are finished. We can compute optimized poses. And we have quite a lot of data that we store about this specific loop closure candidates and the corrected keyframes. We also need the distance map to correct the sim3 error. We'll have a pointer to the calipation as well. Okay, this is interesting. We have a float pointer, idepth map, where the comment is I hate this float pointer. Okay, I can understand that. And we have some hyperparameters like a minimum score to accept and a keyframe gap. I have to say, one of the really nice things about this code is that sometimes there is a little comment that makes me happy. Okay, so besides this loop closing header file, we need also a loop closing CC file in the front end, in the source directory. Loop closing.cc.